Picture yourself standing in the ancient theatre of Epidaurus, high up in the very last row of stone seats, gazing down at the circular stage far below. Someone stands center stage, turns toward the mountains, and whispers, and you hear it, not a muffled sound, not an echo, but every syllable clear and distinct, as if they were speaking right beside you. This isn't a myth or an exaggeration. It's an acoustic reality that has mystified scientists, architects, and visitors for centuries. How did civilizations living over 2,000 years ago, without microphones, without digital sound modeling, without any of the technology we take for granted, achieve something that still feels almost magical today? The answer lies in a breathtaking fusion of intuition, geometry, material science, and deep cultural intention. Ancient builders didn't just stack stones and carve steps, they engineered experiences. They shaped the land and the air itself to carry sound in ways we are only now fully beginning to appreciate with modern instruments. In this video, we're going to unravel those secrets, walking through the same spaces where Greek tragedies moved audiences to tears and Roman orators stirred crowds to action. We'll explore how something as intangible as sound was captured, controlled, and perfected using nothing more than stone, slope, and stunning human ingenuity. This is more than a story about architecture. It's about the human desire to connect, to be heard, and to create spaces where stories and ideas could resonate literally and emotionally across generations. By the time we're done, you won't look at these grand ruins the same way again. You'll see them as they were meant to be seen, not as silent relics, but as living proof of our timeless quest to master the invisible forces around us. So settle in, we're about to step back in time and listen closely to what the past has to say. To understand how these ancient marvels came to be, we have to journey back to their very beginnings. The story of amphitheater acoustics doesn't start with complex blueprints or scientific formulas, but with a simple, powerful human need, the need to be heard. In the heart of ancient Greece, as democracy and drama began to flourish, communities gathered in growing numbers. They needed spaces where a poet's verse could stir the soul, where a philosopher's argument could shape thought, and where a community could feel united by a shared experience. The earliest amphitheaters grew directly from this demand, evolving from simple, flat gathering spots into carefully engineered slopes carved into hillsides. This was not a sudden invention, but a gradual, brilliant process of observation and adaptation. Imagine those early builders. They didn't have textbooks on sound waves, but they had incredibly sharp eyes and ears. They noticed how sound behaved in the natural world. A shout across a valley would bounce back as an echo. A conversation in a secluded cave would sound strangely amplified and intimate. They saw how the natural curve of a rocky outcrop could funnel and focus sound toward a specific point. These weren't just curiosities, they were invaluable lessons in physics, learned directly from the landscape. The first man-made theaters essentially replicated these natural phenomena. By choosing a site nestled into a bowl-shaped hillside, they instantly gained a powerful acoustic advantage. The earth itself became the first wall, containing and projecting sound upward toward the audience. This intuitive understanding was later captured and formalized by brilliant minds like the Roman architect and engineer Vitruvius. In his famous multi-volume work, De Architectura, he dedicated significant thought to acoustics, which he called the voice of a building. Vitruvius laid out principles that seem remarkably advanced even today. He advised that a theater's site must be selected with great care, avoiding places with harsh or dissonant echoes. He understood that the orientation of the stage was critical, recommending it face away from the prevailing winds and the rising sun to prevent the wind from carrying the actors' voices away and the sun from blinding the audience. He even discussed how the very materials used in construction, the density of the stone, the spacing of the seating, would affect the resonance and clarity of sound. His writings give us a window into a sophisticated, empirical science that was being practiced centuries before the formal study of acoustics existed. What's truly fascinating is the holistic approach these ancient engineers took. They weren't just designing a structure, they were designing an experience. Every element worked in concert. The semicircular shape known as the orchestra wasn't just a performance area. Its hard, flat surface acted as a perfect sound reflector. The steeply raked seating did more than just provide a good view. It broke up sound waves to prevent muddy echoes and ensured that each row of spectators was positioned to receive direct sound waves. They were masters of using what they had, harnessing geometry and natural materials like limestone and marble, each chosen for its specific balance of reflectivity and absorption, to create an environment where the human voice could soar. This foundational period, built on keen observation and practical application, laid the essential groundwork for all the acoustic brilliance that was yet to come. But how exactly did they turn a hillside into a precision instrument? The answer lies in the silent, elegant language of geometry. Ancient architects were, in many ways, master geometers. They understood that the shape of a space wasn't just about aesthetics or seating capacity. It was the primary tool for conducting sound. The most common and effective shape they used was the semicircle. This wasn't an arbitrary choice. Picture a stone dropped into a still pond. The ripples expand outward in perfect circles. Now, imagine a sound originating from a single point on a stage. It behaves in a similar way, radiating outward in spherical waves. A semicircular design works with this natural behavior. The curved back wall of the orchestra and the sweeping curve of the seating act as a giant collecting dish, capturing those expanding sound waves and reflecting them back inward, focusing the acoustic energy toward the audience instead of letting it scatter uselessly into the sky. This principle of focused reflection is brilliantly demonstrated at the theater of Epidaurus. Its famous acoustics aren't magic, they're mathematics in stone. The precision of its semicircular curvature is so exact that sound waves emanating from the stage are reflected off the hard limestone seats and the orchestra floor at very specific angles. These angles are calculated not with computers, but through incredible empirical skill, so that the reflected sound waves arrive at the listener's ears just milliseconds after the direct sound wave does. This reinforcement, rather than creating a distracting echo, amplifies the original sound and enhances its clarity. It's the same principle used in modern whispering galleries, where a murmur on one side of a domed room can be heard clearly on the other. At Epidaurus, the entire theater is one giant whispering gallery, ensuring that even the softest sigh or the subtle rustle of a costume from the stage is gathered and delivered to every single seat. Of course, the challenge with any hard, curved surface is the potential for unwanted echoes or sound simply bouncing around chaotically. This is where the genius of the seating design comes into play. The steeply banked rows of stone benches, while appearing uniform, act as a sophisticated diffuser. Each step, each row, and each individual seat breaks up the smooth surface of the cavea. When a sound wave hits this stepped terrain, it doesn't reflect in one single, solid wave. Instead, it's scattered into countless smaller reflections that spread the sound evenly throughout the space. This diffusion prevents the formation of strong, late-arriving echoes that would muddy the speech and eliminates acoustic, dead zones where sound might cancel itself out. It's a perfect balance. The large-scale semicircular shape collects and directs the sound, while the small-scale irregularities of the seating break it up and distribute it fairly to everyone, from the dignitaries in the front row to the common citizens at the very top. This mastery of form reveals a profound, if intuitive, understanding of wave behavior that would not be formally defined by scientists for over 2,000 years. These builders may not have had the equations for frequency or wavelength, but they knew through observation and experimentation that a certain curve produced a certain result. They knew that a steeper slope carried sound higher, and a specific stone density provided the perfect ring. Their amphitheaters stand as monumental testaments to this empirical science, proving that one can harness the laws of physics through careful observation and brilliant design. This geometric foundation was the essential skeleton, but it was the materials they chose to clothe that skeleton in that would ultimately determine the quality and character of the sound itself. But a perfect shape alone was not enough to create the legendary acoustics of these ancient spaces. The geometry provided the blueprint, but it was the very stone itself that gave these structures their voice. The ancient builders were not just architects, they were master material scientists, intuitively understanding that different stones would sing in profoundly different ways. They selected their building materials with the same care a luthier might choose wood for a violin, knowing that each type would shape the sound in a unique and intentional manner. In the great Greek theatres like Epidaurus or Delphi, the material of choice was almost always limestone. This was not a random selection based solely on availability. Limestone possesses a remarkable acoustic property. It strikes a near-perfect balance between hardness and porosity. Its surface is hard enough to reflect sound waves effectively, giving the voice projection and carry. But it is also slightly porous and granular, which means it doesn't reflect sound with the harsh, bright intensity of a perfectly smooth, glass-like surface. Instead, it gently absorbs some of the highest frequencies, those sharp, hissing S sounds that can easily distort into an unpleasant sizzle when over-amplified. This natural filtering effect preserved the fundamental warmth and richness of the human voice and the melodic tones of instruments, allowing the emotional intent of a performance to travel clearly over vast distances without becoming grating or fatiguing to the ear. The Romans, with their appetite for grandeur and imperial spectacle, often turned to marble. Sourced from quarries across their vast empire, marble is far denser and less porous than limestone. Its highly polished, impermeable surface acts as an exceptionally powerful sound reflector. In Roman theatres and Odeons, this created a much brighter, more vibrant, and slightly more reverberant acoustic environment. This brilliance was perfectly suited to the declamatory style of Roman oratory, where a speaker's powerful, ringing voice needed to cut through the air with authority and clarity. It also enhanced the sound of musical performances, adding a layer of shimmering resonance to brass instruments and choruses. This material choice reflects a cultural shift, where the Greeks sought a natural, warm clarity for poetic drama. The Romans engineered a powerful, impressive resonance for civic spectacle. The true craft, however, went far beyond simply choosing a type of stone. The builders paid meticulous attention to how these materials were finished. While we might imagine these ancient theatres built from blocks of perfectly smooth, polished stone, the reality is often more textured. The surfaces of the seats, the stage floor, and the surrounding walls were frequently left with a slight, intentional roughness or were carved with subtle fluting and patterns. This was a deliberate acoustic strategy. A perfectly smooth wall creates a strong, specular reflection, like a mirror for sound, which can lead to sharp, distracting echoes that bounce back and forth. A slightly irregular surface, however, acts as a diffuser. It scatters the sound wave, breaking it into many smaller, weaker reflections that spread the acoustic energy evenly throughout the space. This prevented any single slap-back echo and ensured a smooth, enveloping wash of sound reached the audience, further enhancing intelligibility and creating a more immersive experience. This holistic approach, where every element from the quarry to the final chisel mark was considered for its acoustic contribution, reveals a sophistication that is truly humbling. They understood that to master sound, they had to master the very earth it traveled through. Even with the most perfectly calculated geometry and the most carefully chosen materials, an amphitheater's acoustic success could be completely undone by its surroundings. This is where ancient builders demonstrated another layer of their genius, moving beyond the structure itself to master its relationship with the environment. They understood that the perfect location was not just a flat, empty piece of land. It was an active participant in the acoustic performance. By integrating their design seamlessly into the natural landscape, they turned the entire site into a powerful sound system. The most common and effective strategy was to nestle the theater directly into the slope of a hillside. This was far more than a convenient way to create tiered seating without extensive construction. It was a profound acoustic innovation. The hillside itself acted as a massive, solid baffle, a giant wall that cradled the sound emanating from the stage. Instead of allowing those precious sound waves to radiate outwards and dissipate uselessly into the open air, the earthen backstop contained them, reflecting the energy back toward the audience and creating a natural enclosure. Furthermore, the audience was positioned on an upward slope, which meant the sound source was actually below them. This utilized the natural tendency of sound to travel upwards, much like heat rising. The actors' voices would project forward and upward on a gentle incline, carried effortlessly to the highest seats without them having to strain. The hillside wasn't just a foundation, it was the most fundamental component of the amplifier. But the environment offered challenges as well as advantages, and the ancients were adept at mitigating them. One of the greatest threats to open-air acoustics is wind, which can whimsically snatch words from the air, distorting them or carrying them entirely away from the intended audience. Builders paid close attention to local wind patterns. Through simple, persistent observation, they learned the direction of the prevailing winds for each season. They would then strategically orient the entire theater so that the stage faced away from these winds. This meant the wind would typically be at the actors' backs, pushing their voices forward into the bowl of the theater rather than whipping across the stage and tearing their words away. This same orientation also often served to shield the audience from the sun, preventing glare and keeping them comfortable during long performances, a brilliant example of multifunctional design. We can see this masterful site selection at work in one of the most iconic venues of the ancient world, the Theatre of Dionysus in Athens. Carved into the southern slope of the Acropolis, it is a textbook case of environmental harmony. The massive rock of the Acropolis rises directly behind the seating, providing that crucial solid baffle to contain the sound. The stage looks out northeast, away from the strongest sea breezes that would typically blow from the southwest. And it was situated just below the sacred temple complex, linking the cultural performance directly to the spiritual heart of the city. Every aspect of its placement was intentional, creating a sheltered, focused acoustic environment that allowed the works of playwrights like Sophocles and Aristophanes to be heard with stunning clarity by thousands of citizens. This deep, intuitive understanding of environmental acoustics reveals a philosophy that is often lost in modern construction. For the ancients, architecture was not about imposing a structure upon the land, it was about a conversation with it. They listened to the landscape, learned its rhythms, and then respectfully designed within its parameters. They didn't fight against nature with brute force and technology. They partnered with it, using its inherent properties to achieve their goals. This strategic harmony between built form and natural world resulted in spaces that felt inherently right, both acoustically and spiritually. It was a sustainable, brilliant approach that maximized performance with minimal resources, proving that the most advanced solution is sometimes the one that works with the world, not against it. Yet all this brilliant engineering in stone and slope would have been pointless without a powerful social reason to drive it. The extraordinary effort poured into perfecting amphitheater acoustics wasn't just a technical challenge. It was a direct response to the profound cultural and social needs of ancient society. These structures were far more than mere entertainment venues. They were the beating heart of civic life, the stage upon which democracy, religion, and community identity were performed. In a world without newspapers, radio, or the internet, the amphitheater was the primary medium for mass communication. The clarity of a political speech, the subtle nuance of a tragic actor's delivery, or the precise invocation of a religious hymn, these were not aesthetic luxuries. They were essential to the functioning of the state, the worship of the gods, and the cohesion of the people themselves. Consider the birthplace of theatre in ancient Greece. Athenian democracy was built on the principle of direct participation. Citizens were expected to engage in debates, understand complex legal arguments, and make informed decisions about war and peace. The theatre of Dionysus, therefore, was an extension of the assembly. When a playwright like Aeschylus or Euripides presented a new work, they weren't just telling a story. They were conducting a public debate on contemporary issues: the nature of justice, the abuse of power, the tensions between individual desire and civic duty. For these complex ideas to land, for the moral and philosophical arguments to resonate with thousands of spectators simultaneously, every single word had to be heard with perfect clarity. A muffled line or a lost punchline could mean a failed argument. The acoustic excellence of the space was, in this light, a prerequisite for democratic discourse. It ensured that every citizen, regardless of their seat, was equally informed and equally capable of engaging with the ideas presented. This need for perfect audibility extended powerfully into the realm of religion. Theatrical performances in Greece originated as religious festivals dedicated to Dionysus, the god of wine, ecstasy, and transformation. The plays were acts of worship. The chorus's hymns were prayers set to music, and the actors' dialogues were narratives exploring humanity's relationship with the divine. For these rituals to be effective, for the community to feel a collective connection to the gods, the soundscape had to be immersive and flawless. The audience needed to hear the quiver of fear in a character's voice, the haunting melody of a lament, and the triumphant peal of a divine proclamation. The acoustics facilitated a shared emotional and spiritual experience, binding the community together in a moment of collective catharsis. The architecture itself became a sacred instrument, designed to carry the voice of humanity to the ears of the gods and to bring the messages of the myths back down to the people. The Roman approach, while sharing some similarities, highlights a different set of cultural priorities that equally demanded acoustic precision. The grandeur of Rome was expressed through spectacle and imperial power. The massive amphitheaters and circuses were tools of statecraft. In events like gladiatorial games, the acoustics served a vital practical purpose. The roar of the crowd was a powerful force, a gauge of public opinion that emperors and politicians watched carefully. But for the event to function, announcements of the next match, the introduction of combatants, and the verdicts of officials had to be clearly understood above the din of tens of thousands of excited spectators. Furthermore, the emperor's presence was a central part of the spectacle. His arrival, his gestures, and any words he might speak had to be seen and heard by all, reinforcing his authority and connection to the masses. The acoustics were engineered to ensure that the voice of power could always penetrate the crowd, maintaining order and reinforcing the social hierarchy, even in the midst of chaotic entertainment. Ultimately, the investment in acoustic perfection reveals a deep-seated ancient value, the irreplaceable power of the shared live experience. In our modern world of individualized headphones and digital streaming, we can easily forget the unifying force of a community all listening to the same story, the same speech, the same song, at the exact same moment. The ancient world understood this power intimately. The amphitheater was the amplifier of that collective consciousness. The societal priority placed on acoustic quality was a statement that these moments of shared hearing were worth the immense investment of labor, resources, and ingenuity. It was a declaration that for a society to be strong, its people needed to not just be in the same place, but to truly hear each other and to be heard in return. This profound cultural motivation is what transformed these spaces from simple constructions into acoustic marvels, setting the stage for us to examine the specific architectural features that made this collective listening possible. Now let's zoom in on the very heart of the ancient amphitheater, the stage itself, where the performers and the architecture first met to create the magic of sound. This central performance area, known as the orchestra, was far more than just an empty space for actors to stand. In its original Greek design, the orchestra was a full circle, a precise, perfectly leveled disc of hard-packed earth or stone, often paved with materials like limestone or marble. This circular shape and its unyielding, flat surface were absolutely critical acoustic choices. Think of it like the sounding board inside a grand piano. When a sound is produced on a surface like that, it doesn't just travel upward, it radiates outward in a clean, uniform wave. The hard surface of the orchestra refused to absorb the performer's energy. Instead, it acted as a powerful, horizontal reflector, bouncing the sound waves cleanly off the ground and launching them on their upward journey toward the waiting audience. This ensured that the initial projection was strong, clear, and consistent, giving the sound a solid foundation from which to build. Rising directly behind this crucial orchestra was another architectural masterstroke, the skene. Initially, this was a simple wooden hut or tent where actors could change costumes, but it quickly evolved into a permanent, towering stone backdrop. The skene was the amphitheater's first and most important wall, and its acoustic function was twofold. First, it acted as a massive soundboard. Just as a modern musician uses a reflective shell behind them on a concert stage to project their music into the hall, the solid, flat surface of the skene captured the sound waves emanating from the actors and threw them forward, reinforcing the volume and preventing their voices from being lost behind them. Second, it created an essential acoustic barrier. By enclosing the back of the performance space, it trapped the sound within the audience's area. Without this backdrop, a significant portion of the sound energy would simply have escaped into the open air behind the stage, leaving the audience with a weaker, thinner auditory experience. The skene corralled the sound, keeping it focused where it was needed most. The Romans, never ones to leave a good idea unembellished, took this concept and elevated it to a new level of artistry and acoustic engineering with the skene fronds. This was no plain wall. It was an elaborate, multi-storied architectural facade, often 3 stories high and breathtakingly ornate, decorated with columns, statues, pediments, and a series of deep niches and recesses. While its grandeur was certainly intended to impress and display Roman wealth and power, every curve and column served an acoustic purpose. A single, vast, flat wall, like the early Greek skene, ran the risk of creating a strong, single reflection that could bounce back as a distinct, distracting echo. The complex geometry of the Roman skene fronds solved this problem beautifully. All those columns, niches, and protruding elements acted as a sophisticated natural diffuser. They broke up the incoming sound waves, scattering them into a multitude of smaller, softer reflections that spread throughout the theater in a rich, enveloping blanket of sound. This eliminated harsh echoes while simultaneously creating a more complex and immersive reverberation that added warmth and presence to music and speech. A fantastic example of this principle in action can be found in the surprisingly well-preserved Odeon in Pompeii. This smaller, roofed theater was designed specifically for musical performances and rhetorical contests, meaning its acoustics were paramount. Its skene fronds is a masterpiece of integrated design. The elaborate decoration isn't just applied to the surface, it is the surface. The very depths of the niches and the precise placement of the columns were calibrated to handle the specific sound profiles of instruments and oratory. This created an acoustic environment that was both clear and resonant, allowing the delicate notes of a lyre or the nuanced arguments of a speaker to be appreciated with perfect fidelity by every member of the audience. The design of the Odeon shows us that for the Romans, beauty and function were not separate goals. The grandeur of the skene fronds was directly responsible for the quality of the sound it produced. This intricate synergy between the reflective power of the orchestra floor and the diffusing, projecting power of the stage building created a perfect launchpad for sound, setting the stage for the next critical element, how the audience itself was arranged to receive it. While the stage set the sound in motion, it was the audience's own domain, the vast, sweeping cavea of stone seats, that performed the next critical act of acoustic engineering. This was no simple bleacher. Every single row, every individual step was meticulously shaped and angled not just for viewing, but for listening. The steep, cascading tiers of seating functioned like a gigantic acoustic lens, sculpting the sound waves that reached them to achieve two seemingly contradictory goals: to break up the energy of the sound to prevent muddiness, and to channel it upward with stunning efficiency to ensure no one missed a word. The secret lies in the surface of the steps themselves. If the cavea were one single, smooth, sloping ramp, sound waves would reflect off it in one solid, overwhelming sheet, creating a chaotic roar of overlapping echoes. Instead, the hard edges of each stone bench and the vertical rise between rows created a massively corrugated surface. As sound waves radiated outward from the stage, they didn't hit one flat plane. They encountered thousands of small, angled surfaces. Each step acted as its own tiny reflector, fracturing the sound wave into a spray of smaller, more manageable reflections. This process, known as diffusion, is what prevented the acoustics from becoming a reverberant mess. It scattered the sound energy evenly throughout the entire volume of the theater, ensuring that every listener received a balanced blend of direct and reflected sound, which is the recipe for perfect clarity and presence. But diffusion alone wasn't enough. The sound also needed direction. This is where the precise geometry of the slope came into play. The builders calculated the angle of the cavea with incredible care. It wasn't just steep for a good view, it was steep to create a series of upward-facing reflective surfaces. Imagine the sound wave traveling from the stage and hitting the underside of a stone seat. Because of the steep angle, that sound wave would be reflected not sideways or downward, but upward toward the next row of spectators. This created a cascading effect, where sound was literally bounced from one row to the next, all the way to the top. It was a chain reaction of acoustic energy, guided by stone, that efficiently carried the performance to the farthest reaches of the venue. In the largest amphitheaters, like Rome's colossal Flavian Amphitheater, better known as the Colosseum, this challenge was magnified to an almost unbelievable degree. How could a whisper from the emperor's box possibly be heard by someone in the highest, cheapest seats, nearly 200 feet away and surrounded by 50,000 other people? The answer, once again, was in the gradient. The Colosseum's cavea is astonishingly steep, a vertiginous climb of stone that brings the upper tiers much closer, in a straight line, to the arena floor than a gentler slope ever could. This reduced the distance sound had to travel through the air, where it naturally loses energy. Furthermore, the sheer verticality of the seating meant that the reflective surfaces were angled to shoot sound upward on a much more direct path. The design essentially created a funnel for sound, capturing it at the bottom and efficiently piping it to the top. One of the most fascinating aspects of this engineering is how it was achieved without any modern tools. The architects of these masterpieces didn't have laser levels or computer models. Their tools were empirical, elegant, and rooted in a deep understanding of geometry and the natural world. They used long ropes to lay out the perfect semicircular curves of the cavea, ensuring symmetry. They used the sun's shadows to calculate angles and gradients, marking the passage of time to determine the optimal slope for both sightlines and sound reflection. They built scale models and undoubtedly learned through a process of iteration and observation, listening to how sound behaved in a space and adjusting their designs over generations. This was a pragmatic, hands-on science where the proof was in the hearing. The result was an architectural solution that was both brilliantly effective and beautifully simple, harnessing basic physics through monumental craftsmanship to make sure that in a crowd of thousands, everyone had the best seat in the house. And here's something truly remarkable that reveals just how sophisticated these ancient architects were. They didn't just design their theaters for the stone and the slope. They designed them for the people. They understood that a full house didn't just mean a successful performance. It meant a completely different acoustic environment. All those bodies draped in woolen togas and linen tunics, along with the very fact of human flesh itself, acted as a vast natural sound absorption system. This might sound counterintuitive. Wouldn't a crowd just muffle the sound? In reality, it created the final, perfect ingredient for acoustic clarity. Think of an empty amphitheater. Every surface is hard, reflective stone. A single clap or a spoken word can bounce around for seconds, creating a long, lingering reverberation that turns speech into an indecipherable soup of overlapping echoes. It can be a beautiful, cavernous sound, but it's terrible for understanding the nuanced language of a play or the precise argument of a speech. Now, imagine that same space filled with thousands of people. All those soft, porous surfaces, the clothing, the skin, act like millions of tiny acoustic panels. They soak up a significant portion of the sound energy that would otherwise keep reflecting wildly around the space. They don't absorb the direct sound coming from the stage. They absorb the problematic, late-arriving reflections that cause confusion. The result is a dramatic shortening of the reverberation time. The initial sound from the stage arrives at your ears clean and direct, and the lingering echo is sharply cut off. This transforms a muddy, reverberant space into one with stunning vocal intelligibility, where every consonant and vowel is sharp and clear. This wasn't a happy accident that the ancients simply stumbled upon. The evidence suggests it was a calculated part of the design. Architects like Vitruvius wrote about the importance of proportionality and harmony in their designs, and that very likely extended to anticipating how the space would behave under real conditions when it was alive with spectators. They were designing for the event, not just for the empty structure. Modern experiments in reconstructed ancient venues, like the one at Pula in Croatia, have proven this effect conclusively. Researchers measured the acoustic properties both empty and when filled with audience stand-ins. The difference is night and day. The empty theater exhibits clear, measurable echoes. The full theater, however, achieves acoustic metrics for speech clarity that rival those of a modern, professionally designed lecture hall. The space only truly sings when it is complete, when the audience becomes an active, integral component of the instrument itself. This reveals a breathtakingly holistic design philosophy. The ancient engineers viewed the amphitheater not as a static sculpture, but as a dynamic system. The hillside was the enclosure, the geometry was the conductor, the materials set the tone, and the audience provided the final damping control. Every element worked in concert. They understood that the ultimate purpose of the space was to facilitate a connection between performer and listener, between citizen and community, between humanity and the divine. And they engineered every single aspect, right down to anticipating the acoustic effect of the crowd's clothing, to make that connection as powerful and clear as possible. This deep, intuitive understanding that people were not just passive observers but essential active elements in the acoustic equation shows a level of integrated thinking that we are only now, with our advanced sensors and computers, fully beginning to appreciate. It sets the stage for the final piece of the puzzle, how the performers on that stage learn to work in perfect harmony with this brilliantly engineered environment. Even the most brilliantly engineered space is only half the equation. The ancient amphitheaters provided the stage, but it was the performers themselves who truly brought the sound to life. They were the living, breathing component of this ancient audio system, and they developed a sophisticated arsenal of techniques to ensure their voices would not just reach the back rows, but would resonate with power and emotional truth. This was a physical discipline as demanding as any athletic training, born from the understanding that architecture could only do so much the human instrument had to meet it halfway. Central to this performance tradition was the iconic mask of Greek theatre. While we often think of these masks primarily as tools for visual expression, allowing a single actor to play multiple roles, their acoustic function was arguably just as vital. Crafted from lightweight materials like linen, cork, or carved wood, these masks weren't just faces, they were the first wearable megaphones. The mouth opening was typically fashioned into a small, bell-shaped funnel. When an actor spoke, his voice was immediately captured and directed forward by this built-in horn, concentrating the sound into a focused beam rather than letting it dissipate in all directions. This provided a crucial boost in projection, but perhaps more importantly, it acted as a filter. Just as the limestone seats absorbed harsh high frequencies, the mask's material would subtly dampen certain tones, enriching the voice and giving it a slightly otherworldly quality that cut through the air with clarity and carried the emotional weight of tragic heroes and gods. It was a perfect fusion of art and engineering worn on the face, but a mask alone is useless without the breath and technique to power it. Ancient orators and actors underwent rigorous training in what we would now call vocal projection and breath control. They learned to speak from their diaphragm, not their throats, using the full capacity of their lungs to generate a powerful, supported column of air that could sustain long passages without strain or hoarseness. Rhetoricians like Quintilian wrote detailed treatises on the orator's delivery, emphasizing the importance of varying pitch and pace for clarity and emphasis. They understood that a monotone drone would be quickly lost, while a voice that rose and fell with intention could dance across the acoustics of the space, using the natural reflections to enhance its dramatic impact. This was not natural talent, it was a honed skill, a craft passed down from master to student, ensuring that the human voice could stand as an equal partner to the monumental architecture. Their mastery extended beyond how they spoke to where they stood. Through generations of rehearsal and performance, actors and musicians developed an intimate, empirical knowledge of the stage itself. They discovered the acoustic hotspots on the orchestra floor, specific points where the combination of reflections from the stone paving and the skein wall created a natural amplification. Standing on these precise foci, a performer could feel their voice lift and carry with almost supernatural ease. Conversely, they also learned the dead zones to avoid, areas where sound might cancel itself out or fail to project effectively. This knowledge became part of the traditional stage directions for specific plays, a kind of oral map of the theater's acoustic landscape. A chorus might enter and position itself in a specific arc to maximize the harmonic blend of their voices, or a solo actor would stride to a known sweet spot to deliver a crucial monologue. This strategic movement transformed the performance into a dynamic interplay with the space, a dance where every step was choreographed for optimal sound. Ultimately, this reveals that the legendary acoustics of the ancient world were not a product of architecture alone, nor of performance alone. They were the result of a perfect, conscious collaboration between the two. The builders created an instrument of stone and earth, an instrument that was incredibly responsive and powerful. The performers, in turn, learned how to play that instrument with their bodies and voices. They understood its nuances, its resonances, and its requirements. This synergy between human ingenuity and architectural brilliance is what created the seamless, immersive audio experiences that still inspire awe today. It was a shared effort, a dialogue across disciplines, all in service of one goal: to make sure that every story told, every argument made, and every hymn sung was not just heard, but truly felt by every single person in the vast open-air hall. While the Greeks sought a perfect union with nature, the Romans aimed to conquer and command it, and this fundamental philosophical difference is written in stone and sound across their amphitheaters. The Greek approach was one of harmony. They saw the ideal theater not as a separate building, but as an organic extension of the landscape. The theater of Epidaurus is the ultimate expression of this philosophy. It is not built on the hill, it is carved from the hill. Its majestic semicircle of limestone seats follows the natural curve of the slope, and its stage opens to a breathtaking vista of the Peloponnesian countryside. This design wasn't just picturesque, it was acoustically strategic. The entire structure functions as one unified instrument with the earth itself, using the natural terrain to cradle and project sound with a warm, clear, and surprisingly intimate quality, perfect for the nuanced tragedies of Sophocles and the complex choral odes that required every melodic inflection to be heard. Roman architects, masters of engineering and imperial ambition, had a different vision. While they adopted and respected Greek forms, their goal was often to demonstrate human mastery over the environment through technological prowess. They were not afraid to move mountains, or at least to build their own. The Odeon of Herodes Atticus in Athens, though built by a Greek magnate for a Roman city, is a brilliant example of this Roman spirit. Nestled on the slopes of the Acropolis, it might seem to follow the Greek model, but its defining feature was its grand, wooden roof. This was a monumental innovation. By enclosing the space, the Romans weren't just protecting audiences from the sun, they were creating a completely controlled acoustic environment. The roof acted as a massive reflecting surface, containing the sound energy within the volume of the theater and creating a louder, more reverberant, and powerfully vibrant sound that was ideal for the declamatory style of Roman oratory and the more robust musical performances they favored. This divergence in purpose becomes even clearer when we compare the pure theatrical forms. The Greek theatre was almost exclusively a venue for drama, music, and civic ceremonies, events centered on the spoken or sung word. The Roman amphitheater, most famously embodied by the Colosseum, was something entirely different, a multi-purpose arena for spectacle. Its iconic elliptical shape was designed for visibility to accommodate gladiatorial combats, animal hunts, and mock naval battles, not for perfect acoustics. The acoustic challenge here was immense and of a different kind. The goal was not to preserve the subtle nuance of a whispered line, but to ensure that the roar of the crowd, the blare of trumpets, and the announcements of officials could cut through the incredible din of 50,000 spectators. The sheer verticality of its seating, pushing the upper tiers closer to the arena floor, was a brute force acoustic solution to this problem, a testament to Roman engineering pragmatism. Ultimately, the sound of these spaces tells the story of their cultures. Sitting in the theater of Epidaurus, you hear the clarity of democratic debate and the emotional truth of art, a sound that feels born from the earth itself. In the remains of a Roman Odeon, you can almost hear the echo of power, authority, and technological ambition, a sound contained, amplified, and directed by human will. The Greeks perfected the art of listening to nature and amplifying its gifts. The Romans perfected the art of building a better nature, one where the human voice could ring with imperial command. This evolution from organic integration to technological innovation shows us two brilliant paths to the same destination, setting the stage for us to uncover the hidden mathematical language that made both of these acoustic miracles possible. Behind these awe-inspiring structures lay a hidden language of numbers, a silent symphony of ratios and proportions that guided every curve and every angle. While the ancient world may not have possessed the formal equations of wave theory, its architects were undeniably brilliant applied mathematicians. They operated from a fundamental belief that the universe itself was constructed upon harmonic principles, and that a building, especially one designed for music and speech, must resonate with those same mathematical truths to achieve perfection. This wasn't abstract calculation for its own sake. It was a practical philosophy that connected the order of the cosmos to the experience of an audience member listening to a play. Central to this design philosophy was the pervasive use of certain key ratios, most famously the golden ratio, often represented by the Greek letter phi, approximately 1.618 to 1. This proportion, observed in everything from seashells to the human body, was believed to represent ultimate beauty and harmony. In amphitheater design, this ratio frequently dictated the relationship between key dimensions. For instance, the overall width of the cavea might relate to its height by the golden ratio, or the diameter of the orchestra might be in a harmonic proportion to the distance from the stage to the topmost seat. These relationships weren't arbitrary. They created a space whose dimensions were naturally sympathetic to the harmonic series of the human voice. When a singer hit a certain note, the very geometry of the theater would subtly reinforce that frequency and its related overtones, causing the voice to ring with a warmth and presence that felt almost supernatural. The space itself became a resonant chamber tuned to the fundamental frequencies of performance. The Roman architect and engineer Vitruvius provides our clearest window into this process. In his writings, he describes a fascinating and remarkably clever method for tuning a theater's acoustics using a set of bronze vessels called echaia. These vessels, carefully sized to resonate at specific musical notes, were placed upside down in niches around the theater, effectively acting as Helmholtz resonators centuries before they were formally understood. Even more revealing is his suggestion to use string instruments in the planning stages. he advised that architects should use carefully tuned strings to establish the fundamental dimensions of the theatre, ensuring that the ratios between the length, width, and height of the space were musically harmonious. If the length of the stage was like the string that produces a certain note, then the height of the back wall might be the string that produces its perfect fifth. This created an architectural chord, a building literally in tune with itself. The sound produced within it would therefore be reinforced by the space, not fighting against it. This mathematical mastery extended to the precise layout of the seating. The radial staircases that divided the cavea into wedges, known as cerchides, were not spaced at random intervals. Their placement was often determined by a precise geometric progression, ensuring that the angles of reflection between each wedge were consistent and optimal for channeling sound. The height and depth of each row of seats were also frequently based on a proportional system, creating a rhythmic pattern that further broke up and diffused sound waves in a controlled, predictable manner. Every element, from the grand sweep of the curve down to the individual step, was part of a cohesive mathematical whole. They were building with a deep, intuitive understanding of fractal geometry, where the same harmonious principles applied at every scale, from the largest dimension to the smallest detail. What is most astounding is that this was largely an empirical science. These builders didn't derive these ratios from first principles of physics. They discovered them through centuries of observation, experimentation, and refinement. They built, they listened, and they adjusted. A theatre that worked well became the model for the next one, with its proportions carefully measured and replicated. Over generations, they iterated their way toward acoustic perfection, codifying the successful mathematical relationships into a tradition of design that was both an art and a science. This sophisticated blend of intuition, observation, and mathematical application resulted in spaces that modern physicists can now prove are acoustically exceptional. Their success forces us to reconsider what we mean by scientific knowledge, reminding us that a deep understanding of natural law can be achieved not only through equations, but through the meticulous craft of building in harmony with the world. For centuries, the legendary acoustics of ancient amphitheaters existed in a realm of awe and mystery, supported by anecdotal accounts and the powerful experience of standing in these spaces. But in recent decades, a new chapter has opened in our understanding, one where romantic speculation is being replaced by rigorous scientific fact. Modern acousticians, armed with an arsenal of digital tools their ancient counterparts could never have imagined, are finally able to measure, map, and decode the precise secrets of these stone marvels, confirming just how intentional and brilliant their designs truly were. The primary key to this modern investigation is a process called impulse response measurement. It sounds complex, but the concept is beautifully simple. Researchers take a powerful, sharp sound, like a blank pistol shot or the burst of a balloon, and record it with an array of incredibly sensitive microphones placed throughout the theatre. This initial sound is the impulse. By analyzing how that single, clean sound wave behaves as it travels through the space, how it reflects off every surface, how long it takes to decay, and how its character changes, scientists can create a complete acoustic fingerprint of the entire amphitheater. This data allows them to build a hyper-accurate digital model, a virtual acoustic replica where they can test any sound, from a whispered soliloquy to a full chorus, without ever setting foot on the actual site. It's like having a time machine for sound, allowing us to hear these spaces as they were meant to be heard 2,000 years ago. One of the most compelling case studies comes from the magnificent Roman theatre in Aspendos, Turkey, renowned as one of the best preserved in the entire ancient world. Modern scans and acoustic analysis have revealed that its near-perfect acoustics are no accident. The analysis showed that the slightly convex curvature of the seating area, the cavea, is engineered with incredible precision. This curve acts like a massive acoustic lens, gently focusing sound waves toward the audience and ensuring an even distribution of volume from the front row all the way to the top. Furthermore, the material properties of the local limestone were found to provide an ideal balance of reflection and absorption, particularly for the frequencies crucial to human speech. The scientific data confirmed that the speech intelligibility score in Aspendos rivals that of many purpose-built modern lecture halls and concert venues, a staggering achievement for a structure built without any formal understanding of sound wave theory. This scientific rigor has also served an important role in debunking popular myths. Not every ancient theater was an acoustic paradise. Detailed studies of smaller, less refined provincial theaters, or those that were later modified for different uses, often show significant acoustic flaws like pronounced echoes, dead zones where sound drops out, or poor projection. This is actually incredibly revealing. It shows that acoustic excellence wasn't a guaranteed byproduct of simply building in a semicircle. It was the result of a highly refined, repeatable technique that was mastered in major cultural centers and then disseminated, sometimes imperfectly, across the empire. The variations in quality prove that the best results were intentional, the product of a learned tradition of building that understood the cause and effect of specific design choices. This beautiful collaboration between old and new science does more than just satisfy our curiosity. It provides a crucial bridge connecting the empirical genius of the ancient builders with the analytical power of modern physics. We are no longer just admiring their work. We are beginning to speak their language to understand the why behind the what. By quantifying their achievements, we don't diminish their brilliance, we amplify it, revealing a level of sophistication that demands even greater respect. This fusion of disciplines is giving us a deeper appreciation for these spaces, not just as historical monuments, but as functional masterpieces of design, whose lessons are still relevant for architects and acoustic engineers today. Yet for all the mathematical precision and scientific intention, we must never forget that these were not just performance halls in the modern sense. They were, first and foremost, sacred spaces. The very stones were consecrated, and the air within them was believed to carry more than just sound. It carried meaning, power, and the potential for connection with the divine. The acoustic design we've been marveling at was not merely a technical achievement for entertainment. It was a spiritual technology, meticulously engineered to facilitate transcendent experiences, to evoke raw emotion, and to forge an unbreakable bond between the community, the performers, and the gods themselves. In the Greek world, this sacred purpose is most vividly embodied by the theater of Dionysus in Athens. This wasn't a multiplex, it was a temple to the god of wine, ecstasy, and transformation. The performances held here during the City Dionysia festival were acts of worship, and the acoustics were the medium through which that worship was conducted. Consider the role of the chorus. This group of performers would sing and chant complex hymns in unison, their voices rising as one. The crystal-clear acoustics ensured that every harmonic layer of their song, every word of these poetic prayers, reached every single member of the audience with perfect fidelity. This wasn't about hearing a nice song. It was about a shared, immersive sonic bath that could induce a collective emotional state. The clarity was believed to be a conduit, a pure channel that allowed the essence of the prayer to travel unimpeded to the ears of Dionysus and the other gods, and for their divine presence to felt in return. The audience wasn't just watching a play, they were participating in a ritual, and the architecture's ability to carry every subtle tremor of emotion in an actor's voice or every haunting note from an aulos, a double reed instrument, was what made that participation so powerful and real. The Romans, while often more pragmatic, understood this symbolic power of sound just as well, though they channeled it toward different ends. For them, amplified sound was a direct tool of statecraft and imperial cult. In the vastness of the Roman Forum or the Circus Maximus, the ability of a priest's or an emperor's voice to ring out with authority and clarity was not just practical, it was a manifestation of their divine right to rule. The sound itself became sacred. When an announcement was made about an omen from the gods or a victory dedicated to Jupiter, the acoustics ensured that the message was not just heard, but that it landed with awe-inspiring force. It created a sense of inevitability and divine sanction. The voice of power was engineered to be unmistakable, unignorable, and larger than life, reinforcing the social and cosmic order with every projected syllable. The sound path from the speaker to the listener mirrored the hierarchy itself, a single, powerful source transmitting truth downward to the receptive masses. This spiritual dimension reveals a deeper layer of intentionality in the design. The very path of sound through these spaces often mirrored ancient cosmological beliefs. In many cultures, the circular orchestra represented the cosmos or the sacred center of the world. The sound originating from this point would radiate outward in perfect, harmonious waves, symbolizing the divine order emanating from the center to the periphery, enveloping all of society in its embrace. The seating arrangements themselves could reflect social hierarchies, with the best acoustics often reserved for the seats of priests and dignitaries closest to the action, placing them symbolically and literally closer to the source of the sacred sound. Understanding this transforms our view of these structures from being clever machines into being profound philosophical statements carved in stone. They were physical models of a universe where everything was connected through harmonic vibration, where a community could literally sit within and listen to the working of a divinely ordered world. This rich symbolic purpose, woven seamlessly with acoustic science, makes their enduring power all the more comprehensible and reminds us that the most advanced engineering often serves our deepest human needs for meaning and connection. While the grand stages of Epidaurus and the Colosseum rightly capture our imagination, some of the most fascinating acoustic secrets are hidden in the less celebrated amphitheaters scattered across the ancient world. These regional venues tell a different story, one not of monolithic perfection but of ingenious local adaptation, where builders tailored their designs to specific environments, available materials, and unique cultural needs, proving that acoustic literacy was a widespread, vibrant tradition. Take the magnificent Roman theatre in Orange, France, a UNESCO World Heritage Site that stands as one of the best preserved examples of its kind. Its most commanding feature is the towering, intimidatingly vast stage wall, the Schiene Frons, which soars over 100 feet high and remains almost entirely intact. This was not merely for imposing decoration, it was a colossal acoustic instrument. In the often windy conditions of southern France, this massive stone facade acted as a gigantic, immovable sound shield. It protected the performance area from crosswinds that could otherwise tear the sound away from the audience, while its sheer, flat surface served as an enormous reflector, hurling the voices of actors and the music of performers forward with immense power and clarity into the seating cavea. The design at Orange represents a regional solution to a local environmental challenge, a brute force and brilliantly effective approach to sound projection that is distinct from the more integrated, hillside-hugging designs of Greece. Then there are the smaller, more intimate spaces that highlight a different priority altogether, nuanced acoustics for smaller gatherings. Consider the Bouleuterion in Ephesus. This was not a theatre for grand spectacle but a covered council house where the city's leaders met to debate weighty matters of law and policy. Here, the acoustic goal was absolute speech intelligibility for a select, seated audience in an enclosed, rectangular hall. Without the benefit of a vast, open sky to dissipate sound, the architects faced the challenge of echoes and muddiness. The solution likely lay in a sophisticated combination of wooden roofing, which provided absorption to control reverberation, and carefully angled seating that ensured direct lines of sight and sound between every orator and listener. The acoustic strategy here was one of precision and clarity for political discourse, a world away from the emotional reverberance desired for dramatic performance. It shows us that the ancients understood different acoustic environments were needed for different purposes, and they possessed the skill to create them. Perhaps one of the most intriguing adaptations is found in the smaller, roofed venues known as odeons, which were specifically designed for musical performances and poetic recitals. Unlike their open-air cousins, these structures often incorporated wooden roofs. This was a revolutionary acoustic choice. The wood provided a lighter, more absorptive surface than stone, which would have shortened the reverberation time, creating a drier, more intimate sound that was perfect for appreciating the intricate melodies of a lyre or the subtle nuances of a recited poem. The roof also created a contained environment, trapping the sound energy within the space and allowing for a softer dynamic range. Musicians didn't need to project to the heavens. They could play with expression and delicacy, knowing the architecture would carry it. This attention to the specific needs of music reveals a granular understanding of how different sound sources behave and what acoustic environment best serves them. From the wind-battling wall of orange to the music-cradling roof of a typical odeon, these lesser-known sites paint a picture of a vibrant and diverse acoustic landscape. They prove that ancient innovation was not a single, secret formula passed down from a master architect, but a living, evolving practice. A widespread literacy of sound that was adapted and applied with stunning creativity from one city and one purpose to the next. This very adaptability makes the eventual loss of such profound knowledge all the more poignant. Yet for all its sophistication, this profound understanding of sound and space was not destined to last forever. The slow unraveling of the Roman Empire, with its decaying trade routes, fading central authority, and shifting societal priorities, began to sever the direct line of architectural tradition that had been passed down for nearly 1,000 years. As Europe fragmented and entered what we now call the Middle Ages, the very purpose of large public building underwent a radical transformation. The world no longer needed vast open-air theatres for civic gathering or dramatic spectacle. The new imperatives were defense and divinity, fortification against invasion, and the construction of churches that reached toward the heavens. The pragmatic, human-scaled acoustics of the amphitheater were largely forgotten, replaced by an architectural language that spoke of power and prayer in a different key. The great Gothic cathedrals that rose to dominance were acoustic marvels in their own right, but they pursued an entirely different sonic ideal. Where the ancient builders sought clarity and directness, Gothic architects embraced reverberation and mystery. Their soaring vaults, immense naves, and hard, reflective surfaces of stone and glass were designed to create a long, lingering echo, sometimes lasting 10 seconds or more. This was not a flaw, it was a feature. The enveloping, blurring wash of sound was intended to dissolve the individual words of the Latin Mass into an indistinct, heavenly chorus, a sonic representation of the ineffable glory of God. The experience was meant to be overwhelming and transcendental, not intelligible in a literal sense. The precise acoustic science of Vitruvius, focused on the human voice and human connection, had no place in this new vertical world. The knowledge didn't just fade, it became functionally obsolete for the needs of the time, preserved only in crumbling manuscripts that few could still read or apply. The reawakening began centuries later, during the intellectual and artistic fervor of the Renaissance. A renewed fascination with the classical world sent scholars and artists scouring monastic libraries for ancient texts, and among the most influential finds were the rediscovered writings of Vitruvius. His 10 books on architecture became a Bible for Renaissance thinkers, providing a direct window into the lost principles of Roman engineering and design. Architects like the great Andrea Palladio in Italy studied these texts with reverence, seeing in them a path to recapture the harmony and proportion of antiquity. Palladio's work, particularly his design for the Teatro Olimpico in Vicenza, stands as a monumental act of acoustic rediscovery. Although built indoors, this stunning venue is a conscious revival of the Roman theatre form, complete with a deeply sculpted schiene fronds and a semicircular seating arrangement. The design was a direct application of Vitruvian principles, and while its enclosed nature creates a different sound than an open-air amphitheater, it proved that the geometric and proportional ideas of the ancients could still be harnessed to create powerful, engaging spaces for performance. It was the first crucial step in reconnecting a broken chain of knowledge. The true full circle moment, however, would wait for the tools of modern science. The real revival of interest in ancient acoustic techniques didn't gain full momentum until the 20th century, when the field of architectural acoustics became a formal scientific discipline, and archaeologists began to apply its methods to the ancient world. Pioneers like Wallace Clement Sabine, who developed the formula for reverberation time, gave researchers the quantitative tools to measure what the ancients had achieved empirically. Suddenly, they could go beyond admiration and begin to analyze. Acoustics was born as a dedicated field, using sophisticated equipment like the impulse response measurements we discussed earlier to create digital acoustic blueprints of ancient sites. This scientific validation transformed the conversation from one of myth and mystery into one of measurable fact. We could now prove that the acoustic properties of Epidaurus were not a legend but a reproducible reality, a triumph of design that could be studied, understood, and even emulated. This modern revival is a beautiful collaboration across millennia. Today's acousticians and archaeologists don't just look at these ancient theaters as ruins, they see them as a vast, open-air laboratory of acoustic innovation. By studying the specific angles of reflection, the material compositions, and the precise geometries, they are reverse engineering the decisions of the ancient builders, learning the why behind the what. This isn't merely an academic exercise. This rediscovered knowledge is incredibly relevant, offering timeless lessons in sustainable, passive sound design that requires no electronic amplification. The ebb and flow of this acoustic knowledge, from its empirical peak in antiquity to its obsolescence in the Middle Ages, to its scholarly rediscovery in the Renaissance, and finally to its scientific validation in the modern era, is a powerful story of how human understanding can be lost and found again. It sets the stage for us to see how these ancient secrets are now inspiring a new generation of architects to build spaces that are not only beautiful but sound truly magnificent. The wisdom of the ancient amphitheater is far from being a relic confined to history books. It is alive and well, actively shaping the soundscapes of our modern world. Today's architects and acoustic engineers are increasingly turning away from solely relying on electronic amplification, looking instead to these age-old principles of passive acoustic design to create spaces that are not only more sustainable but also more naturally immersive and authentic. This isn't about mere historical imitation. It's a sophisticated fusion of ancient intuition with modern computational power, applying the core tenets of reflection, diffusion, and strategic material selection to solve contemporary auditory challenges. The goal is to craft environments where sound feels organic and integrated, whether for an open-air concert, a university lecture, or even the digital realm of virtual reality. One of the most direct and beautiful homages to this ancient legacy can be experienced at the Getty Villa in Pacific Palisades, California. This museum, dedicated to ancient Greek and Roman art, features an outdoor classical theater that is a meticulous reimagining of its historical counterparts. The designers didn't simply borrow the aesthetic, they engineered its acoustics with deliberate intent. The theater employs a steeply raked, semicircular cavea carved into a hillside, using the natural slope to project sound upward. The stage building, or skene, is constructed from materials chosen for their specific reflective properties, acting as that crucial soundboard to throw the performers' voices toward the audience. Attending a performance here is like stepping into a living laboratory of ancient science. The clarity is startling. Without a single microphone, a whisper from the stage can be heard in the last row, a powerful demonstration of how effective these 2,000-year-old design principles remain. It proves that the most advanced acoustic technology isn't always a black box of electronics sometimes. It's the intelligent arrangement of stone, slope, and space. But the influence extends far beyond replica theaters. The fundamental ideas are being adapted in countless innovative ways. Consider the modern lecture hall at a university. Instead of burying the space in carpet and acoustic tile, which can deaden sound and create a lifeless atmosphere, architects might design a gently curved rear wall lined with carefully profiled wooden panels. These panels act as modern diffusers, scattering sound waves evenly throughout the room, just like the stepped seating of an ancient cavea, ensuring every student receives clear, direct audio from the professor. This reduces the need for loudspeakers at the back of the room and creates a more natural, engaging learning environment. Similarly, concert halls now frequently incorporate irregular surface textures on walls and ceilings, a concept directly descended from the slightly rough-hewn stone of ancient theaters, to break up sound waves and eliminate harsh echoes, creating a richer, more enveloping musical experience without relying solely on electronic enhancement. Perhaps the most futuristic application lies in the world of virtual and augmented reality. Developers creating immersive digital environments face the challenge of simulating realistic soundscapes. To make a virtual ancient Roman forum feel authentic, they can't just use a generic echo effect. They need to accurately model how sound would behave bouncing off specific marble columns, traveling across a stone pavement, and being absorbed by a crowd of digitally rendered people. By feeding the precise geometric and material data of ancient structures into acoustic simulation software, they can create incredibly accurate audio models known as convolution reverb algorithms. This allows someone wearing a VR headset to not only see a reconstruction of the theater of Dionysus, but to hear a performance within it exactly as an ancient Athenian would have, with all the subtle reflections and resonances that the architecture provides. In this way, ancient acoustic principles are now being used to bring history to life for our ears, creating a bridge across millennia through the science of sound. This movement towards passive design is also a profoundly sustainable one. Electronic sound systems consume significant energy, require complex manufacturing, and generate e-waste. A well-designed passive acoustic space, on the other hand, uses zero energy to amplify sound once it is built. It leverages the immutable laws of physics, baked into its very structure to work perfectly for centuries with minimal maintenance. This represents a shift in philosophy from constantly powering and updating technology to creating intelligent, permanent structures that work in harmony with their environment. The ancient builders were the original masters of sustainable design, using local limestone and the existing landscape to achieve their goals. Today's architects, armed with a deeper scientific understanding but inspired by the same principles, are following in their footsteps, proving that the most resonant solutions are often those that have already stood the test of time. To truly grasp the genius behind these ancient designs, we need to listen to the science itself, to understand the invisible dance of sound waves that these builders learned to choreograph so masterfully. At its core, sound is simply energy traveling through the air in waves, much like ripples moving across the surface of a pond after you toss in a stone. When one of those ripples, a sound wave, encounters a barrier like a wall or a stone seat, it doesn't just stop. It interacts with that surface in one of three fundamental ways, and the ancient architects became intuitive experts in managing all three. The first and most straightforward interaction is reflection. This is exactly what it sounds like. The sound wave hits a hard, flat surface and bounces off, much like a rubber ball thrown against a wall. In an amphitheater, the vast, curved-back wall of the stage building, the skene, was a giant reflector. Its purpose was to catch the sound waves radiating backward from an actor and bounce them forward toward the audience, effectively doubling the acoustic energy sent into the seating area. But reflection has a potential downside. If it's too strong and comes from a single, flat surface, it can create a distinct, delayed echo. You've experienced this if you've ever shouted in a large, empty gymnasium and heard your voice come bouncing back at you a split second later. That delayed echo is incredibly disruptive to understanding speech, as it overlaps and muddles the direct sound coming from the source. This is where the second concept, diffusion, becomes the ancient builder's secret weapon. Diffusion is the art of scattering sound. Instead of a sound wave hitting one flat wall and bouncing off in one single, strong reflection, a diffusive surface breaks that one wave into countless tiny, weaker reflections that spray out in many different directions. Imagine the difference between shining a laser pointer at a mirror versus shining it at a disco ball. The mirror gives you one single, intense beam of reflected light. The disco ball, with its thousands of tiny, angled facets, scatters that light all over the room in a beautiful, even sparkle. The ancient builders created their own version of an acoustic disco ball through texture and shape. The slightly rough, unfinished surfaces of the limestone seats, the fluting on columns, and the all-important step design of the seating itself, each row, each step, each edge acted as one of those tiny facets. They shattered incoming sound waves, spreading the acoustic energy evenly throughout the entire space. This prevented those loud, distracting echoes and instead created a smooth, enveloping blanket of sound that reached every listener from multiple angles almost simultaneously, reinforcing the direct sound without blurring it. The third piece of the puzzle is absorption, which is the process of sound energy being swallowed up and converted into a tiny amount of heat, rather than being reflected. In a modern recording studio, you see this in the form of thick foam panels on the walls that deaden the sound. The ancients had a more dynamic approach to absorption, the audience itself. As we discussed, the clothing and bodies of thousands of spectators acted as a massive, natural absorption system, but the materials played a role too. While stone is primarily reflective, the specific type of limestone chosen for many Greek theaters has a slight porosity to it. This minute roughness doesn't just diffuse sound, it also absorbs a tiny amount of the highest frequencies, those sharp hissing sounds that can easily become distorted and unpleasant when over-amplified. This gentle filtering effect preserved the warm, rich tones of the human voice, making it easier on the ear over long performances. The ultimate goal of managing these three phenomena, reflection, diffusion, and absorption, was to achieve something acousticians call a short reverberation time with strong early reflections. Reverberation time is simply how long it takes for a sound to fade away in a space. For clear speech, you want that time to be very short, so syllables don't blur into each other. The audience and the materials helped achieve this, but you also want strong, early reflections. These are the first sound reflections that reach your ears, arriving just milliseconds after the direct sound from the stage. Your brain seamlessly merges these early reflections with the direct sound, perceiving it all as one single, louder, richer, and clearer signal. The Ancient Amphitheater was perfectly engineered to deliver a powerful flood of these beneficial early reflections from the diffusive surfaces of the cavea, while the audience absorbed the later, problematic reflections that would cause echo. The result was that a listener received a reinforced, clarified version of the performance, as if the very architecture was leaning in to whisper the words along with the actor on stage. This intricate balance, achieved through stone and slope rather than digital processors, is the true physics behind the magic, a testament to an empirical understanding of wave behavior that would not be formally defined for millennia. This extraordinary acoustic environment did far more than just allow performances to be heard. It fundamentally shaped the art that was created within it. The knowledge that even the slightest whisper or the most delicate pluck of a lyre string would be faithfully transmitted to every listener empowered ancient playwrights and composers to craft works of breathtaking subtlety and emotional complexity. In a space without this clarity, an actor might have to bellow and declaim, reducing a character's inner turmoil to a shouted monologue. But in the acoustic embrace of the Greek theater, an actor could afford nuance. A hesitant pause, a voice cracking with grief, a conspiratorial whisper shared with the audience, these subtle inflections became powerful theatrical tools because the architecture guaranteed they would land. The playwright Euripides was a master of this, crafting characters whose psychological depth was revealed through intimate, strained dialogue rather than grand proclamation. In his play Hippolytus, the title character's tortured speeches of guilt and shame rely on a vocal performance that can shift from defiance to despair in a single breath, a performance that would be utterly lost without the theater's ability to carry every emotional tremor. This symbiotic relationship extended powerfully to music. The ancient Greek aulos, a double-reed instrument often compared to an oboe, could produce a wide range of sounds, from raucous, energetic melodies to soft, mournful tones. Composers knew that the softer, more melancholic passages would not be wasted. A musician could play with dynamic variation, confident that the quieter, more expressive sections would travel just as effectively as the loud ones, allowing for a much richer and more varied musical narrative to accompany the drama. This capability encouraged a sophisticated interplay between speech, song, and instrumentation that became a hallmark of Greek tragedy. The choral odes in Sophocles' Oedipus Rex are a perfect example. They are not simple songs, they are complex poetic structures set to music, where the chorus moves between chanting, singing, and rhythmic movement. The acoustics allowed each layer, the meter of the poetry, the melody of the music, and the specific words being sung to remain distinct and intelligible, creating a multi-layered emotional experience for the audience. The art form evolved to its highest complexity precisely because the architecture could support it. We can even see this influence in the world of Roman comedy, particularly in the works of Plautus. His plays are famous for their rapid-fire dialogue, elaborate puns, and witty wordplay. This style of comedy is entirely dependent on acoustic clarity. A pun that is missed is a joke that falls flat. The complex, quick-paced banter between characters, full of misunderstandings and double entendres, requires the audience to hear every single syllable clearly to follow the comedic rhythm. The reflective, bright acoustics of a Roman theatre, enhanced by marble and the grandiose skinny fronds, were perfectly suited to this verbal dexterity. It allowed the performers to articulate with speed and precision, ensuring that the linguistic humor, a cornerstone of Plautine comedy, hit its mark with every member of the vast audience. The architecture didn't just amplify the performance, it actively enabled a specific, sophisticated style of writing and acting that would have been impossible in a less resonant space. This profound interplay reveals that the amphitheater was not a passive container for art but an active collaborator in its creation, pushing the boundaries of what was possible in live performance and leaving a legacy of artistic achievement that was literally built upon a foundation of acoustic science. Preserving the magnificent soundscapes of these ancient amphitheaters is a battle against time, nature, and our own best intentions. The very elements that give these structures their character, the specific density of their limestone, the precise texture of their surfaces, the perfect geometry of their curves, are incredibly vulnerable. Primary enemy is simple weathering. Centuries of rain, wind, and freeze-thaw cycles slowly erode the stone. A seat that was once sharp and angular, perfectly designed to diffuse a sound wave, becomes smooth and rounded over hundreds of years. This gradual wearing away might seem minor, but on an acoustic level, it's like slowly sanding down the teeth of a key. Eventually, it won't turn the lock anymore. The subtle, calculated irregularities that broke up echoes are lost, and the acoustic performance can become noticeably more reverberant and less distinct. Perhaps the most complex challenge comes from our own desire to help through restoration and reconstruction. When a section of seating collapses or a part of the stage wall is damaged, the instinct is to repair it. However, sourcing an exact material match is often impossible. The original limestone might have come from a quarry that has been exhausted for 1,000 years. Modern concrete or newly cut stone from a different region will have a completely different density, porosity, and surface hardness. Swapping out an original block for a new one is like replacing a single, precisely tuned string on a grand piano with one from a different instrument. It will never sound quite the same. That new stone will reflect sound at a different intensity and absorb different frequencies, creating an acoustic dead spot or an unnaturally bright reflection that subtly disrupts the harmonious balance the original builders achieved. A well-intentioned repair can inadvertently create a patchwork of acoustic inconsistencies. Then there is the constant hum of the modern world. Ancient theaters were carefully situated away from urban noise, but today's cities have expanded right up to their gates. The gentle rustle of leaves and the distant sound of sheep that were the original background noise have been replaced by the relentless drone of traffic from nearby roads, the buzz of tourist helicopters, and the chatter from nearby cafes. This modern noise pollution creates a constant, low-level acoustic mask that makes it harder to perceive the subtle reflections and delicate carry that define the space's true acoustic character. Even the sounds of preservation itself can be damaging. The vibrations from heavy machinery used for archaeological work or conservation can, over time, cause microfractures in the ancient stone, further altering its properties. The biggest paradox, however, is the impact of the people who come to cherish these places, us. Tourism is essential for funding preservation, but the sheer volume of visitors presents a constant dilemma. The shuffling of feet, the rustling of bags, and the cumulative effect of thousands of people touching the stones every day contribute to wear. More significantly, the acoustic experience is now almost always heard with a background murmur of guides and tourists, a far cry from the focused silence of an ancient audience. Managing this requires an incredibly delicate balance. How do you make these sites accessible to the world without loving them to death? How do you allow people to experience the magic without their presence fundamentally changing it? Some projects are pioneering innovative solutions to these challenges. At the Ancient Theatre of Syracuse in Sicily, conservators have adopted a principle of minimal intervention, using detailed laser scans to identify stones that are critical to the acoustic function and focusing their efforts on stabilizing them in place rather than replacing them. In other cases, acoustic monitoring has become a standard part of site management. By taking detailed impulse response measurements before and after any restoration work, conservators can now scientifically quantify the acoustic impact of their actions, ensuring they are preserving not just the visual appearance of the theater, but its sonic soul. This careful, scientifically informed stewardship is our best hope for ensuring that the whispers from these ancient stages continue to be heard for centuries to come, guiding us toward the digital tools that now offer a powerful new way to safeguard this intangible heritage. But what if we could step beyond the physical limits of preservation and truly travel back in time to hear these spaces as they were meant to be heard on the very day they opened? This is no longer the stuff of fantasy, thanks to a revolutionary digital frontier that is merging cutting-edge technology with ancient craftsmanship. Researchers are now using high-precision laser scanners to capture every minute detail of these amphitheaters, from the grand sweep of the cavea to the microscopic wear patterns on an individual seat. This process, called LiDAR, creates a point cloud map of billions of individual data points, forming a perfectly accurate digital twin of the entire structure. This incredibly detailed 3D model becomes the foundation for something even more extraordinary, an acoustic simulation. Using sophisticated audio software, scientists can then assign specific acoustic properties to every single material in the virtual model. They tell the program that this section is hard, reflective limestone, that section is slightly more absorptive marble, and another is the porous texture of weathered stone. Then they can virtually place a sound source, a speaker or a musical instrument on the digital stage and thousands of virtual microphones throughout the seating. With a click of a button, the software calculates the complex journey of the sound wave. It models how it will reflect off every surface, how it will diffuse across the stepped seats, how it will be absorbed by the virtual audience, and how all these individual sound paths will combine and arrive at the listener's ear. The result is an impulse response, a unique acoustic fingerprint for that specific spot in the theater. By applying this fingerprint to any recorded sound, they can make it sound as if it is being performed right there in the ancient space. Initiatives like the ambitious Rome Reborn project are bringing this experience to the public in breathtaking ways. They allow anyone with a VR headset to not just see a visually stunning reconstruction of ancient Rome, but to take a virtual walk through a perfectly rendered digital amphitheater. And the experience is not silent. You can stand on the stage and speak, hearing your own voice project and ring through the space with an authenticity that is spine-tingling. Or you can take a seat in the highest tier and listen to a pre-recorded performance of a Greek chorus, experiencing the precise clarity that defined ancient drama. This technology is a powerful preservation tool, creating a permanent, perfect digital record of a site's acoustic properties at a specific moment in time, protecting it against any future damage or decay. But more than that, it is the ultimate educational instrument. It demolishes the barrier of time, allowing students, historians, and enthusiasts to not just read about these acoustic marvels, but to truly experience them, fostering a deeper, more intuitive understanding of the ancient world's technological prowess. This ability to literally hear the past opens up incredible new possibilities for research and appreciation, allowing us to finally listen in on the symbolic and cultural layers that were so carefully engineered into every stone. Yet for all the mathematical precision and scientific brilliance, these structures were never just machines for sound. They were powerful symbols carved in stone, their very acoustics serving as a profound metaphor for the cultural values that built them. In a world without microphones or mass media, the ability for a single voice to be heard clearly by thousands was nothing short of miraculous, and this miracle was imbued with deep meaning. The flawless transmission of sound became a physical representation of ideals like truth, transparency, and divine order. An architect designing an amphitheater was not merely solving an acoustic puzzle. He was crafting a space where communication itself was sanctified, where words could travel from one to many without distortion or obstruction. This was the ultimate symbol of a society that believed in the power of the spoken word to shape reality, to govern justly, and to connect with the gods. We can see this symbolism expressed in two profoundly different ways through the lenses of Greek and Roman culture. In the democratic city-states of ancient Greece, the amphitheater was the great equalizer of voice. The design ensured that a playwright's critique of a leader, a philosopher's challenging argument, or a common citizen's reaction from the cheap seats held the same acoustic weight. The sound traveled with impartial clarity to every listener, from the honored officials in the front row to the farmers and merchants in the very last tier. This wasn't just a technical feat, it was a physical manifestation of the democratic ideal of Ischouria, the equal right to be heard in public debate. The architecture itself guaranteed that a message's power derived from its truth and emotional resonance, not from the social standing of the speaker. The collective experience of hearing the same words with the same clarity fostered a sense of shared understanding and civic unity, reinforcing the very foundations of participatory government. The Roman approach, by contrast, channeled acoustic perfection into a symbol of imperial power and hierarchy. In the vastness of the Roman Forum or the colossal Flavian Amphitheater, the primary voice meant to be heard with unmistakable clarity was that of authority. The ability of an emperor's pronouncement, a general's victory speech, or a priest's sacred invocation to ring out and reach every corner of a packed venue was a stunning demonstration of control. It was a sonic manifestation of the emperor's far-reaching power, his voice literally unable to be ignored, echoing the reach of his legions and the inevitability of his rule. The acoustics reinforced a vertical social order, a single, powerful source of sound transmitting truth downward to the receptive masses. In a culture where the emperor was increasingly seen as a divine figure, this flawless projection could also be interpreted as a metaphysical phenomenon. The leader's word, like the will of the gods, was omnipresent and undeniable, filling the entire space and leaving no room for dissent. The architecture thus became a tool for manufacturing consensus and awe, using the physics of sound to cement a political and spiritual reality. This symbolic layer transforms our understanding of these spaces from impressive engineering projects into profound cultural statements. The precise curve of a seating section wasn't just about sound waves, it was about shaping a societal experience. The choice of gleaming white marble for the stage wall wasn't merely for reflection, it was about creating a brilliant, awe-inspiring backdrop for the voice of power. Every architectural decision carried this double meaning, blending practical function with deep cultural metaphor. The amphitheater became a microcosm of the universe as that society understood it, whether a universe of democratic equality and shared discourse, or one of imperial order and divine authority, all expressed through the invisible yet perfectly orchestrated movement of air. Recognizing this symbolic purpose adds a rich human depth to the stone and mortar, reminding us that the most enduring structures are always those that resonate not just with sound, but with meaning. Of course, the grand narrative of ancient acoustics is not a simple story of universal perfection. For every Epidaurus that leaves us breathless with its auditory clarity, there are dozens of other sites that serve as a humbling reminder of the very human process of trial and error that underpinned this architectural revolution. These less-than-perfect venues are not failures. They are perhaps an even more valuable part of the historical record, offering us a raw, unfiltered look into the workshop of ancient engineering, where mastery was hard-won through iteration and sometimes frustrating missteps. Walk through the remains of a smaller, provincial theatre in the outskirts of the Roman Empire, far from the cultural and economic powerhouse of a city like Rome or Athens. The difference is immediately apparent and often audible. The semicircular shape might be slightly off, a little too flat or a little too tight, breaking the precise harmonic geometry that allows sound to travel so efficiently. The seating might be shallower, with a gentler slope that fails to lift the audience high enough to receive those cascading reflections. Or the materials might be purely local and pragmatic, a softer, more porous sandstone that absorbs too much sound energy, leaving voices flat and lifeless before they can reach the upper tiers. These provincial theatres tell a story of knowledge dissemination. They show that the exquisite principles perfected in the capital cities were like a recipe that could be slightly altered with each retelling. A local builder might have heard descriptions of the great theatres or seen rough sketches, but without the direct guidance of a master architect or the resources for perfect stone, the execution could fall short. They prove that acoustic expertise was a specialized craft, not a universal given, and its application across the vast ancient world was wonderfully, revealingly uneven. Some flaws, however, were born from success and expansion. As the Roman Empire repurposed older Greek theatres for new types of spectacles, they often made modifications that inadvertently damaged the original acoustic balance. A famous example is the addition of a velarium, the massive canvas awning stretched over an amphitheater to shield spectators from the sun. While a marvel of engineering in its own right, this enormous fabric canopy acted as a giant acoustic absorber. It would soak up the precious sound energy that the hard stone surfaces were designed to reflect, significantly dampening the overall volume and shortening the reverberation time that gave music its richness. In a space designed for the clear, sharp projection of the human voice, this could create dead zones, particularly under the deepest parts of the awning, where the sound would feel muffled and distant. It was a classic trade-off, comfort for acoustic purity, a compromise that the sports-loving Romans were likely more than willing to make. Then there are the acoustic ghosts of later modifications, changes made long after the original architects were gone. In many sites, you can see where medieval or even later communities moved in, using the amphitheater as a ready-made fortification or a source of building materials. Walls were built across the orchestra, blocking the critical sound path. Seats were ripped out, destroying the intricate diffusive surface of the cavea. In some cases, entire theatres were buried over centuries, their lower sections preserved while their upper walls were quarried for other projects. When these sites are excavated and partially restored, the acoustic picture is inevitably fragmented. A modern visitor might stand on the stage and hear a strange, lopsided echo, a phantom of the original soundscape now haunted by missing walls and altered sightlines. These imperfections are a palimpsest of history, showing us not a single moment of perfect design, but the long, messy life of a structure adapting and sometimes succumbing to the changing world around it. This honest appraisal, far from diminishing the achievements of the ancients, actually makes them more impressive and more relatable. It reveals the process. It shows us that the acoustic marvels we admire were not created in a single, divine moment of inspiration, but were the pinnacle of a long evolutionary climb. Each flaw, each dead zone, and each echo in a lesser theater represents a lesson learned. A builder in one city might have noticed how a certain curve created a problematic reflection, and his successor, working on a new project 50 years later, would adjust the angle to compensate. This cumulative knowledge, passed down through generations of apprentices and written into the stone of each new project, is the true story of ancient acoustic science. It was a living, breathing discipline of observation and adaptation, proving that even our most brilliant ancestors were human, learning step by imperfect step how to make the air itself obey their command. This fascinating story of acoustic mastery isn't confined to the Mediterranean world. A remarkable pattern emerges when we look across the globe and across centuries, revealing that the drive to harness sound through architecture is a truly universal human impulse. Completely isolated from the Greeks and Romans, other sophisticated cultures independently discovered the same physical principles and engineered their own stunning sonic spaces, often for strikingly similar ceremonial and spiritual reasons. This isn't a case of shared blueprints, it's a case of shared human ingenuity, a collective reaching for the same acoustic truths hidden in the laws of physics. Consider the great Mayan ball courts of Mesoamerica, like the immense court at Chichen Itza. To the untrained eye, it's a long, narrow alley flanked by towering, sloped walls. But stand in the center of that stone court and clap your hands just once. The sound that comes back is not a simple echo. It's a bizarre, almost synthetic chirping sound that seems to ripple through the air. This is no accident. The precise geometry of the court, the parallel walls, their specific angle of incline, and the distance between them creates a series of rapid, cascading reflections. The sound wave doesn't just bounce back once. It pinballs between the walls, breaking up and recombining in a way that creates a distinctive auditory signature, a phenomenon known as a flutter echo. Archaeologists and acousticians now believe this wasn't just a curious byproduct. In the context of the sacred ball game, a ritual that often represented a cosmic struggle between life and death, this strange acoustic effect likely had profound ritual significance. The sound of the rubber ball striking a player's hip or the stone wall would have been transformed into an otherworldly reverberation, a sonic manifestation of the supernatural forces believed to be at play during the game. The court itself became a ritual instrument, its acoustics amplifying the spiritual drama for all participants. On the other side of the world, in the arid regions of India, we find another breathtaking example of acoustic innovation in a most unexpected place: stepwells. These are not merely sources of water. They are monumental inverted temples, intricate labyrinths of steps and galleries carved deep into the earth, descending to the water table. The architecture of these stepwells, with their precisely symmetrical staircases and their long, parallel hard stone surfaces, creates a perfect environment for a phenomenon known as the whispering gallery effect. At a site like the Chand Baori in Rajasthan, a whisper uttered softly at one end of a step can be heard with startling clarity by someone standing hundreds of feet away at the opposite end. The sound skims along the hard stone surfaces, losing very little energy as it travels through the still, sheltered air of the well. While the primary purpose was water collection, the acoustic properties were almost certainly integrated into the social and spiritual life of the community. These were cool, sheltered gathering places for women, and the ability to communicate privately across vast distances in a murmuring undertone would have been powerful. Furthermore, in a sacred context, a priest chanting or ringing a bell at the water's level would have had their voice and music amplified and carried upward, enveloping all those on the steps in an immersive blanket of sound, turning a practical structure into a place of profound auditory experience. What makes these global parallels so compelling is the complete independence of their development. The Maya had no contact with the builders of Indian stepwells, and neither had ever heard of Vitruvius. Yet they all arrived at the same fundamental understanding, that specific shapes, parallel walls, steep angles, hard materials produce predictable and powerful acoustic effects. This points to a deeper truth about human engagement with our environment. It suggests that our ancestors everywhere were not just passive inhabitants of their world. They were active listeners and brilliant experimentalists. They learned by doing, by observing how sound behaved in a canyon or a cave, and then they applied those lessons to their own constructions. They understood that architecture could do more than just house or protect. It could shape experience, evoke emotion, and facilitate a connection to the divine through the controlled manipulation of something as intangible as sound. This shared historical thread reveals a universal human fascination with controlling our sonic environment, a quest for acoustic perfection that transcends culture, geography, and time, proving that the desire to make our voices carry and our rituals resonate is a fundamental part of the human story. The journey to understand ancient acoustics is far from over. In many ways, it feels like we are only just beginning to listen. The frontier of this research is being reshaped by a new wave of technologies that promise to peel back layers of history we never knew existed. Imagine applying artificial intelligence to the vast digital models we've created of these amphitheaters. An AI could run millions of acoustic simulations in the time it takes a human to run one, testing variables we haven't even thought to consider. It could answer questions like, did the original builders apply subtle, now invisible surface treatments to the stone? Were certain sections painted with specific plasters or resins that altered their reflective properties? We know the ancients were master material scientists. Perhaps they had finishing techniques that have been completely erased by time, and AI could help us reverse engineer those lost recipes by analyzing microscopic residues and predicting their acoustic impact. This high-tech investigation extends to the very atoms of the structures. Advanced material analysis, using tools like portable X-ray fluorescence spectrometers and ground-penetrating radar, allows us to understand the stone itself on a molecular level without damaging a single ancient block. We can now map the precise density, porosity, and mineral composition variations across an entire theater. This can reveal why builders might have chosen a specific type of limestone for the stage and a different one for the upper seats, a choice that would have fine-tuned the sound for different audience sections. We can also start to investigate long-term climate adaptations. How did the acoustic properties of a theater in the dry, hot climate of North Africa differ in its design from one in the cooler, more humid coastal regions of Turkey? By correlating material data with historical climate records, we might discover that ventilation channels or specific orientations weren't just for comfort, but were sophisticated tools for managing how sound traveled through air of different temperatures and densities, a factor that significantly affects the speed of sound. The most exciting progress, however, is happening at the intersections between disciplines. The era of the solitary archaeologist working alone is giving way to vibrant collaborations where acoustic physicists sit down with classicists, and data scientists work alongside experts in ancient music. These interdisciplinary teams are asking entirely new kinds of questions. For instance, what was the exact acoustic impact of the audience? We know they acted as absorbers, but was there an ideal crowd size for each venue? Could the builders have calculated a perfect ratio of human absorption to stone reflection? And perhaps most intriguingly, how did the specific musical scales and instruments of the time influence the architecture? The ancient Greek musical system was built on tetrachords and modes that sound very different to our modern Western ears. Did the architects tune the dimensions of the orchestra or the spacing of the seats to resonate perfectly with the most important notes and intervals of their music, creating a space that was literally in harmonic sync with the performances it hosted? These are not just academic puzzles. The answers have profound implications for how we build today. In an age obsessed with sustainability, the ancient world offers a masterclass in passive acoustic design, creating perfect sound without a single watt of electricity. By uncovering their secrets, we can inform the design of new concert halls, lecture theaters, and public spaces that are both acoustically brilliant and environmentally conscious. The future of ancient acoustics is therefore a two-way street. We are using tomorrow's technology to listen more closely to yesterday's achievements, not simply to admire them, but to bring their timeless wisdom into the buildings of our future. This ongoing conversation between the past and the present ensures that the voices from these ancient stages will continue to inform and inspire us for generations to come. From the whispering galleries of Epidaurus to the grand echoes of the Colosseum, these ancient structures are far more than silent ruins. They are a powerful testament to a forgotten science, a brilliant fusion of human intuition and the immutable laws of physics. We've walked through their sun-drenched steps, tracing how every curve of stone, every choice of material, and every strategic placement was a deliberate act of acoustic engineering, all achieved without a single microchip or digital amplifier. We've seen how these innovations were fueled by profound cultural needs: the Greek desire for democratic clarity, the Roman drive for imperial spectacle, the universal human yearning for spiritual connection. We've discovered how performers became masters of this built environment, and how modern science, with all its advanced tools, has only confirmed the breathtaking precision of their empirical designs. The true legacy of these spaces extends far beyond their historical wonder. They offer us urgent lessons for our own time. In an era of booming speakers and energy-hungry sound systems, these amphitheaters stand as a masterclass in sustainable, passive design. They show us that the most elegant solutions often work in harmony with nature, not against it, using the landscape itself and the innate properties of local materials to create experiences that are both powerful and perfectly integrated. They remind us of the irreplaceable power of the shared, live experience, the magic that happens when a community gathers in one space, all listening to the same story at the same time, connected by the simple, profound act of hearing together. So the next time you walk into a modern concert hall, a lecture theatre, or even a grand public square, take a moment to listen. Listen to how the space shapes the sound. Is it clear and enveloping, or muddy and distant? Think about the invisible architecture of the air around you. The ancient quest to master sound isn't confined to history books. It's a continuing conversation about how we connect with one another. These stone marvels challenge us to build not just for the eye, but for the ear, creating environments that foster understanding, inspire emotion, and remind us of the beautiful, invisible force that connects us all. We'd love to hear which of these ancient secrets most amazed you. Was it the geometric genius, the material science, or the cultural purpose behind it all? Share your thoughts in the comments below, and if you enjoyed this journey into the echoes of history, be sure to subscribe for more adventures into the world's greatest